Hello all, welcome to the course on Strength of Materials 2. So Strength of Materials 2 is the advanced course for civil engineering students. It deals with stresses, strains, deflections in structural elements. Today I am going to deal with a torsion of circular shafts. I am Supraja, Assistant Professor in the Department of Civil Engineering, BVRIT, Narsapur. So, first one, coming to the definition of torsion. Torsion means it is twisting or torsional moment. So, whenever we talk about torsion, it is such that we have a twisting. This can be explained by using a simple diagram. So, this is shaft, this is bearing. Shaft is supported by a bearing. It is inserted into the bearing. When we apply torque on the shaft, so it will resist an opposite torque by the bearing. So due to this opposite torques, the shaft will be twisting. So torque is also called as twisting or torsion. So torque will be defined in terms of mathematical form. So let us consider this is the shaft of radius r and this is torque. So now torque can be defined as it is the tangential force. It is the product of tangential force and radius of the shaft. So T can be written as tangential force Ft into radius of the shaft. Now coming to the units for torque. So it is the tangential force, unit of force is Newton and radius of the shaft is meters or millimeters. Now coming to the derivation of torsion equation. So torsion equation is T by J is equal to tau by R is equal to G theta by L. Here T is nothing but twisting moment or torque. J is nothing but polar moment of inertia. Tau is nothing but shear stress produced by the shear force. R is the radius of the shaft. G is modulus of rigidity. Theta is angle of twist. L is the length of the shaft. Now this equation can be derived by using simple definition of modulus of rigidity and simple mathematics. Now let us consider a shaft at one end fixed, and this is the central axis of the shaft, and length of the shaft as L and the cross section of the shaft as this and the radius of shaft as R. Now after applying some torque T, so this will be rotates at one end. So let us assume this point as this angle as theta and this point as B and this point as B dash and this point as A. Now from the diagram, we can write tan phi is equal to BB dash by AB. We know that AB is equal to length of the shaft from the diagram. Now, for smaller angle of phi, we can write tan phi as phi. Now, phi is equal to BB dash by AB is the length of the shaft. Now, we can write BB dash is equal to L into phi. Now, let us consider this is the radius of the shaft. This is the position B before application of torque, and this is B dash after application of torque T, like this, and this is angle theta. Now from this we can write length of the arc BB dash will be radius of the shaft into theta. Now let us consider this is equation 1, this is equation 2. Now from the principle of modulus of rigidity, basic definition of modulus of rigidity is G is equal to shear stress by shear strain. Now G can be written as shear stress is tau and shear strain as phi. Now from equations 1 and 2 we can write L alpha is equal to R theta. Now phi can be written as R theta by L. Now we can substitute phi in equation 1. Now G is equal to tau by phi is R theta by L. Now we can write G is equal to L tau by R theta. Now from this we can write tau by R is equal to G theta by L. Now this is the first phase of torsion equation. Now coming to the second phase of torsion equation, consider a cross section of the shaft, and this is the origin or center of the shaft. Now let us consider a small element at a distance r from the small r from the center of the shaft, and capital R is the radius of the shaft. Now from the definition of shear stress, tau is equal to shear force by shear area. Now we can write tau is equal to F by A. Now force acting on the element will be dF is equal to shear stress into area of the element. We can find out the torque on element will be dt is equal to dF into radius of the element, distance of the element from the center of the shaft. This is from the definition of torque. Now we can write dt is equal to dF as tau into area into r. Now from phase 1 of torsion equation or torque equation, that is tau by r is equal to g theta by L. Now from this we can write tau as g theta by L into radius of the shaft. Now dt will be g theta by L into R into area into R. Now for smaller distances, for smaller radius of the element, we can replace capital R as we can replace a small r as capital R. Now we can write torque acting on the element dt can be written as force acting on the element multiplied with distance or radius of the element from the center of the shaft. Now we can write dt as shear stress into area into radius of the element. Now from the first portion of torsion equation, we know that tau by r is equal to g theta by L. Now dt can be written as, from this tau will be g theta by L into radius of the shaft. Now dt will be g theta by L into r into area into radius of the element. Now for small radius of the element, we can replace small r as capital R. Now dt can be written as g theta by L into smaller into area into smaller. Now for total torque acting on the shaft can be find out by using the integration on both sides. Now integral dt will be integral g theta by L into R into area into R. Now integral dt will be g theta by L is the constant into integral r square into area. Now we know that integral r square as polar moment of inertia, that is J. Now we can write T is equal to g theta by L into J. From this we can write T by J is equal to g theta by L. Now from equations A and B, we can write T by J is equal to tau by R is equal to g theta by L. Now this is called as torsion equation. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.